One of the goals of CDIO is to foster deep learning. So I'll be talking to you about 3 strategies that I used in a course. I'll talk about the course a little bit later to foster deep learning, and I'll try to hypothesize on why it works. One of the strategies worked better than the other ones. So I'll just talk to you a little bit about the school I work for, École de Technologie Supérieure, because it's different from most of the engineering schools. It's a state university, so there's no policy for selecting students other than they must have the required diploma. We have about 307 students, undergraduate students, engineering students, in 7 different programs. Now, what's special about our school is that all, or 90% of the students come in as technicians, and they come out as engineers. So when they come in, they have a big bagage of procedural knowledge. They know how to do things. But as engineers, we have to complement that knowledge with conceptual knowledge, a lot of conceptual knowledge, and conditional knowledge also. So conceptual knowledge is the what of things. What is something? Conditional knowledge would be, in what conditions do I use this knowledge, or do I use this procedure? And unfortunately, we don't spend much time teaching conditional knowledge. We spend a lot of time teaching conceptual knowledge in general as professors, a little bit about procedural knowledge depending on what type of school you are, what type of engineering faculty you are. Another characteristic of our students is that they are more inductive than deductive. Like to start with small pieces of knowledge or small pieces and build theory on that, whereas most professors are rather deductive. You start with general principles and then work down to the particulars. So there's a difference in teaching style and learning style for the students. So there's different ways to deal with this, and I'll talk to you about a mandatory course in mechanical engineering, but that doesn't really matter. That's not the point. The fact is that there's 3 hours of theory and 3 hours of lab, and during the lab they learn how to use 2 software, or one programming software, which is MATLAB, which is used principally to solve nonlinear equations, and ANSYS, which is a finite element program. So they're very good at learning how to use these packages or these software. They are often not aware why they make the choices they make. Why do I select this type of element, for example, when I'm creating a model? They'll replicate the examples they have. They'll replicate the exercises we give. It's not really a conscious choice. And the reason for that is that because they lack the theoretical or conceptual knowledge and the conditional knowledge to be able to make those choices well. They also told me that they had difficulty preparing for exams because during the lectures everything flows well, and when it comes time to study, they're overwhelmed. And in that course, at the beginning of the semester, we give them 3 projects. So we give them the description of the 3 projects at the first course, and we explain them, and then go through an exercise of what type of knowledge do you think you need to do this, and that introduces the subjects for the courses, and it motivates them. But they still have difficulty applying the knowledge to those problems. So the solution to this problem was to have them study on a regular basis, so that the knowledge wouldn't just build up, and then they'd have to cram it for exam or cram it to do the projects. I used 3 different strategies during 3 different semesters, trying to improve each one. So the first one was to have them map future knowledge. So they would have to read the class material beforehand. Didn't work very well. We'll see. So then I asked them to map past knowledge, what we'd seen the week before. That worked a little bit better. And third time, I gave them a choice of either writing up a summary. Sure, they're fairly comfortable with writing summaries. They're less comfortable with mapping techniques. So write up a summary, draw a map, or attend a 10-minute quiz. Now, the first challenge I met was, what type of map do I ask them to draw? Are you familiar with mapping? Mind mapping, concept mapping, knowledge mapping? Okay, some of you are, some of you are not. So I'll go a little through this. I'll present 4 types of maps. The first of which is a mind map. Now, mind maps are characterized central idea with secondary ideas radiating from the first, and then they continue radiating. So you can see that my maps are a type of graphical representation with other types of representation. And on the right-hand side, I put 4 types of maps with increasing richness of information, increasing complexity as we go on. So that's my map. Now, if the mind map starts to look a little bit more like a network, if you have links across the different branches, that becomes a topic map. So here's an example. A concept map is a little bit more difficult to draw because a concept map has to be composed of nodes, which represent the concepts, and links, which represent the relationship between the concepts. Concepts are usually verbs. The linking words are usually, nouns, and the links verbs. Now, a difference between a concept map and a knowledge map or knowledge model is that knowledge can be of different type. It's not only concepts. And here is a knowledge map. So in the knowledge map, we differentiate the different types of knowledge. So here I have a procedure. How do you model knowledge? It's a procedure. And to be able to do that, you need some input, the different knowledge types, which are facts, procedures, concepts, and principles. And you need different types of links that between those types of knowledge, and that is regulated by a grammar. And the model can be made either by a top-down or bottom-up method. So you can see here that a knowledge map is even more complex. I found that the knowledge map was just too complex for students. It needs formal training to be able to do this. So I decided to ask the students to make a topic map. Now remember, the first time was asking the students to draw a map of future material. Now what happened is that during the first 2 weeks it worked well because the students could link new class material to other class materials or math courses. And but after a few weeks, the material was so new that they had difficulty creating those links. And the maps just looked like a tree of the chapter headings. That was all there is. the second implementation, I asked to draw a map of prior knowledge, so what we had seen the week before. Now, there was one advantage in there, that the map quality was sustained or maintained during the semester, meaning that they could create those links between what they'd seen the week before and what they had learned beforehand. And mid-semester, I did a informal evaluation of the course. I asked them to write on a sheet of paper 3 things they liked about the course and 3 things that they didn't like or wanted improved. 37 of them didn't mention anything. They didn't matter. It didn't matter to them. 8 students said that they appreciated mapping. They adopted it readily. 3 said that they didn't mind, and 6 students said that they didn't like it. And why? Because they had difficulty. And we have to recognize that it is difficult to map, and it takes about a 4-week to 5-week period before students feel comfortable with mapping. And some students will not get it. They will have lots of difficulty. Some students thought it was not strategic enough. They said that it did not help them get a good mark at the exam. I could talk about this, but I won't go into the details. And other students said that they prefer work in a team. This was an individual assignment they had to do every week. Now, the third implementation, smaller class, I asked, the students were given the choice of writing a summary, drawing a map, or attending the quiz, 10-minute quiz. Now, there were some very interesting results. Only 2 students elected to write summaries. All the other students, not all, but 24 students drew maps. 7 students did neither. They only attended the quiz. But what's interesting is that all the students either handed in a summary or drew a map, also attended the quiz. And they did very, very, very well on the quiz, whereas the 7 other students didn't do well at all. 2 of them dropped out, and the five who kept had the lowest marks, the 5 lowest marks by the end of the semester. Another added benefit is that there was an incredible increase in the quality and the quantity of class interaction. I teach a lot by asking questions all the time. And with that class, the response was phenomenal. I always had somebody volunteer an answer, and it wasn't always the same person. And by giving them the choice, there was no more complaints about having to map. Students had the choice. And another benefit, classes started on time because of the quiz. Now, why would that third implementation work much better? Novak, who was who was about to implement concept mapping, says that about 15% of students will resist mapping, 15% students will embrace it. So that explains part of the results I had, but I went to look at motivation theory. Now, Yo, researcher in Quebec, who looked into this, said that motivation is conditioned by 3 variables: the student's perception of control, do they have control over their learning, of their perception of capability, and their perception of value. Depending on the 3 implementations, these variables had either a low value, or have high value, or medium. Now, what I think happened is that because deep learning requires intrinsic motivation, this is reported in the literature, and intrinsic motivation is determined by the perception of the sense of control, the value of the learning activity, and the to succeed. By giving them the choice of methods, writing a summary, mapping, or taking a quiz, there was an improved control. They could choose the method they wanted. The students who did the mapping or wrote the summaries and attended the quiz, they had immediate feedback on the value of that activity. And because they succeeded well in the quizzes, it heightened their sense of success. And it worked towards building that intrinsic motivation that's required for deep learning. So in conclusion, I think that motivational factors are very important and affect the effectiveness of the student performance. An irritant that still stayed in the third implementation is that it was done individually. So one way of going around that would be to ask teams of students to build a map together. And some limitations of this study is that it's qualitative, had small populations, and really go further, I'd need to develop metrics to measure the quality of the work they were producing. Thank you.